Chinsky and the corresponding chapter in the second volume. Okay, so we're going to start discussing toroidal compactifications of string theory. Now, I know that when we started discussing the heterotic string, we had some discussion of toroidal compactifications. We're going to do it again and do it more cleanly and better this time. Okay. So the first part of this lecture will be a reminder, and then we'll move on to some new material. Okay. So in the first part of this lecture, what we're going to do is to just look at something very simple. In the first part of this lecture, what we're going to do is to look at just the free boson. Okay. So we have X. So suppose there's just one free boson. So we have X, which is identified with X plus 2 pi r. So that our free boson, our spatial direction, is not flat space but a circle. As I said, we've discussed some of this before, but I'm going through it again just so that you remember what we need to go further. Okay, let's remember how this impacts the mode expansion of X. Okay, so what we did here, so first notice that in the mode expansion for X, we had the zero mode and the oscillators. Okay, this part here is purely a statement about the zero mode, because if you take this X and expand it in zero mode plus cosine or sine or something of sigma, okay, this clearly is about the part independent of sigma. So it's purely about the zero mode. So the first conclusion that we draw immediately by looking at this statement is that all that is affected about the conformal field theory of the string by identifying this thing in field space is the zero mode. Oscillator part is unchanged, and we're not going to talk about it. Okay? So now let's see how the zero mode is affected. There is one obvious effect and one less obvious effect. The obvious effect went this way. Look, the obvious effect went this way. First, we have X is equal to, let's say we just substitute in some X naught of t. Okay? Then you remember that the Lagrangian, which was 1 over 4 pi d2x, d2 sigma del alpha x becomes 1 over 2 alpha prime x naught dot square. Okay? So what is the spectrum of the zero mode part of this guy? The spectrum of the zero mode part of this guy is, well, if you take this and quantize it, of course we get the spectrum which is alpha prime by 2 p squared by 2m, m is 1 by alpha prime, and the wave function corresponding to this is e to the power I p x naught. But this wave function has to be periodic, as it has to be single valued. That should be meaningful. It should give you a single answer for x naught, irrespective of whether you choose x naught or x naught plus 2 pi r. Okay, so it must be that e to the power I p into 2 pi r is equal to 1, which means that p has to be equal to n by r. Okay, so the obvious modification in the zero mode sector is that the continuum of momenta that were previously there is replaced by the following discretum. P is n by r. This is the same thing that would happen if we were looking at a particle propagating on a circle. It's not very new. Okay? The new thing which we also talked about when we last talked about circle compactification is this. The fact that this was a string tells us that in addition to, it's not just that it constrains the old expansion. You're allowed new things, new configurations that were not allowed before. Now, what do I mean by that? Look, suppose I have x as a function of sigma. We know that when, let's say I start from 0 and I come back to 2 pi, x has to come back to itself. Previously, when x was uncompactified, it meant that x of 2 pi was x of 0. But here, because x is not uncompactified, what it really means is that x of 2 pi is equal to x of 0 plus 2 pi r times w, where w is any integer. Right? Because
you are saying there is a difference between cylinder and identifying just two boundaries?
No, I mean it is a cylinder.
Yes.
It's just that a string that starts at 0 can wind around and come to itself. That's a perfectly allowed configuration. But it could wind on once, or two, or twice, or 3 times, or 4 times, or it could wind on -1, -2, -3. So the w could be any integer lying from -infinity to infinity. Okay? Now, so what we have to do is to quantize the string separately in each w is an integer. Different values of w are discretely different. At least on the cylinder, the w is never going to change, because for w to change, the string would have to break, and strings can't break. In a theory with no open strings, at least, strings can't break. We'll come back to theories with open strings where they can break. Is this clear? Okay, so in each w sector of the theory we've got, w is like a super selection sector as far as the cylinder theory is concerned. You fix w once and for all, and then you quantize the theory. What I've told you so far is what happens in the sector w equals 0, because that was the only sector available in the uncompactified theory. But now we've got an infinite number of new sectors, so we have to quantize the theory in each sector. Is this clear? Now, how do we do that? You might think, okay, now there's an infinite number of new jobs to do, but it's not that difficult. The first question, it's not that difficult because everything's quadratic.
Is compactified all
Mu's, at the moment we're saying one of the x's is compactified. There are more interesting things that can happen when 2 or more are compactified. But we'll come back to that. At this level, of course, there will be a winding number in the first direction and a winding number in the second direction. Okay? But there are interesting things that happen, new additional enhanced gate symmetries. We'll come back to that as we go. Okay? All good? You had a question?
For different w, the quantization will be different.
It's just a different theory in a way. Each w is its own game. As we will see soon.
Physically, they are totally different.
They're totally different. In this sector, you have to quantize the string when it winds once, which is different from quantizing the string when it winds twice. Okay? However, because this theory is so simple, it will turn out to be not very different. Okay? So let's look at how it works. First thing we're going to do is to see how we can solve this boundary condition. So what I'm going to do is to try to find a configuration that obeys this boundary condition and is also a solution to the string equations of motion. The x equations of motion. X equation of motion is simply del squared x is equal to 0. One simple solution for del squared x equals 0 is x being linear. Any function that's linear in sigma obeys del squared x equals 0. And we want to satisfy that x of 0 is x. So now it's something very simple. Take x is equal to r times sigma. So that times w. This is a configuration that solves the equations of motion. Okay? It's a configuration that solves the equations of motion and obeys the boundary conditions. So let's suppose I take this plus x tilde and I plug it into the action. Now, the whole theory is quadratic. Okay? Now you can see either by logic or by calculation that the quadratic theory has no cross terms between this and this. It's got no cross terms because the object, this configuration, obeyed the equations of motion. So the variation of x around this had to vanish, which means lack of cross terms for a quadratic theory. Okay? And of course, it's very easy to see by direct calculation as well. So the whole action becomes the action for this plus the action for this. Now the action for this is very easy to compute. Okay? So S is equal to, okay, S is equal to, okay, S is equal to, the action for this is, let's see, it's 1 by 4 pi d2 sigma into x dot square term we can ignore. So it's WR square, because just the x prime square. So the integral over sigma gives 2 pi. So we get W squared R squared by 2 dt d tau. Okay, so this sets some effective energy for the string. Is this clear? Okay. So now, in addition, of course, we've got the usual expansion. So we've got this plus the stuff coming from sigma tilde. Now, what are the boundary conditions for sigma tilde? X has to, sorry, x tilde. X has to obey the boundary condition here, but this already obeys that boundary condition. Therefore, x tilde is periodic. So x tilde is quantized just like
oscillators,
just like a periodic scalar, but it continues to have its zero mode identified in this way.
Yeah.
X naught, I've not written, x naught is equal to x naught plus 2 pi r. Right? And therefore, what we said here applies to x tilde. Is this clear? With w equals 0. That's what we analyzed on the left hand side of the board. We'd analyzed the problem with a periodically identified scalar, but with w equals 0. So the only effect of w here, the only effect of w is adding this extra term, w squared r squared by 2, into the action. Okay? And therefore we conclude that now let us be a little more serious. Suppose we were working in Minkowski space. Then this theory would have had x dot squared minus x prime squared. So this would have come with a minus, so this would have come with a minus, because minus x prime squared. And this would have come with a minus. But in a Minkowski space action, the action is t minus v. So minus this tells us that there is an energy which is plus that amount. Okay? So basically, the only difference between having this compactified direction and not is that the energy, which is L0 plus L0 bar. Okay? L0 plus L0 bar. What does it become? It becomes w squared r squared by 2 plus alpha prime by 2 n squared by r squared. And then Everything else, the remaining the oscillators are just totally unaffected. It's the old story. Is this clear? Now we're going to come back and analyze this a little more systematically. So let us look at the solutions. Okay, oscillators are untouched, so I'm not even ever going to write them. Okay? What was the solution for x, the classical solution for x, in the configuration in which the momentum was n by r, and the momentum was n by r, and the winding number was w. So let's write down what x was. Well, from winding, it was x was equal to w r sigma. That we'd already know. And you remember the relationship between p and x dot. That comes from the action being x naught dot squared by 2 alpha prime. So p is the canonical momentum conjugate to x naught. So is equal to x naught dot by alpha prime. Okay? So p is equal to x naught dot by alpha prime. And therefore, we should write plus p alpha prime tau, right? Because then x naught dot by alpha prime would give us p. But p was n by r. Okay? So in the zero mode sector, this was the expansion of x. Now, when we were analyzing conformal field theory of the free boson, it was useful to divide things into parts that depended on sigma plus and sigma minus. So you remember we had sigma plus was equal to tau, let's say minus sigma, let's call that minus sigma plus was equal to tau plus sigma. And we may have used opposite conventions last time, doesn't matter. Okay, let's reword this in terms of sigma plus and sigma minus. So x here is equal to WR. Now sigma
plus minus sigma minus.
Exactly. Sigma plus minus sigma minus over 2 and plus alpha prime n by r sigma plus plus sigma minus divided by 2. And therefore we have x is equal to sigma plus into WR by 2 plus alpha prime n by r plus sigma minus into WR by 2 minus. Okay, yeah. Let's do the let's do alpha prime n by r minus WR. Okay. And there's half.
Yeah, then the WR over 2. I mean, it will just be W.
Thank you. WR. Okay. Previously, this was just the statement, when W was 0, this was just the statement that the momentum was shared half into the sigma plus part and half into the sigma minus part, because everything came with a tau, and tau was written as tau plus sigma plus tau minus sigma by 2.
Yeah.
So PL and PR were equal, and they were both equal to P by 2.
Yeah.
Now we've got an interesting effect. If we call this P plus or P, I'm not sure. Okay, I'll call it P plus. I think Pulchinski calls it PL and PR. Okay, we call this PL, P plus, we find WR plus alpha prime n by r. Well, let's write it as alpha prime n by r. I mean, we still have the half momentum, but then we have a shift with the winding. And P minus is equal to half into alpha prime n by r minus WR. Okay, so we still have the half, but we've got the opposite shift in P minus. Okay. Now, something that we should notice is the following. Okay. Okay. Firstly, is this clear? Okay. So in the when you've got a circle with winding, the 0 mode sector is specified by specifying 2 integers. Okay, and the 2 integers are the momentum integer and the winding integer. Quantization of the string tells us that the left moving momentum and the right moving momentum defined in the following way, that the coefficient of sigma plus and the coefficient of sigma minus, okay, are given by these quantities. Let me see if Polchinski defines them with the half or not. We should stick to his conventions. He n by r plus w by alpha prime. So, okay. So now let us go to Polchinski's conventions. So according to Polchinski, x is equal to p L sigma plus by 2 plus p r sigma minus by 2. PR is with a minus. Yeah, perfect. Okay, so with these conventions, I'll just go to PL and PR. PL and PR are this without the half, because the half appears in the definition. Okay, so right. Okay. And then with this convention, L0 is equal to, he claims, let's check this, alpha prime PL squared by 4 plus NL, left moving oscillator number. And L0 bar is equal to alpha prime PR squared by 4 plus NR. Now let's check this by checking that with all these conventions, if we add these up, we get this. Okay, so we've got alpha prime by, so L0 plus L0 bar is equal to alpha prime by 4 into PL squared plus PR squared. But PL and PR we've written here. So that gives us, yes, so we get WR additional 2. So all good. Okay, so these are our formulae along with these formulae for PL and PR. Okay.
And alpha prime.
Alpha prime.
There should be an alpha prime to make up for the dimensions.
Yeah. Now, Polchinski then probably puts the alpha prime out here. Just a minute. Yeah. He wants PL to be n by r. and therefore he puts alpha prime out. Sorry.
And therefore, then in W there will be an alpha prime.
There will be an alpha prime
W1 over alpha prime.
over alpha prime. Perfect. Because, yes, perfect. Thank you. Thank you.
Yeah, alpha prime has dimensions of length squared.
Length square. Perfect. Perfect. Okay, great. Okay. Now, there are many interesting things about looking at strings moving on circles, but the main focus of the interest in today's lecture is this phenomenon called Tduality, which I want to focus on. Again, I told you about it last one lecture, but we're going to say it again so that what we're going to do, what we're heading towards is doing Tduality for open strings and discovering d-branes. But I just want to make sure you remember the story about Tduality for closed strings before we do that. Okay. So good. Now, one thing that one thing that's easy to see is the following. Suppose we do the following. Suppose we take one theory with R and another theory with R prime, which is equal to alpha prime by R. Okay. Now, let me compare the zero mode contributions. In fact, let me compare L0 and L0 bar. Or in fact, let me compare the X itself in these two theories. Okay. So in the first theory we had X is equal to alpha prime by 2 into W, N by R plus WR by alpha prime sigma plus N by R minus WR by alpha prime sigma minus. Right? In the second theory, we have X, let's call it X prime, let's call this R tilde. X tilde is equal to alpha prime by 2 into N by R tilde plus WR tilde by alpha prime.
Now N and W will...
Ah, right, N tilde and W tilde. Thank you. Sigma plus N tilde by R tilde minus W tilde R tilde by alpha prime sigma minus. Now, let us substitute what R tilde is in terms of R. So this becomes alpha prime R, and this becomes this R tilde 1 by R. This here becomes alpha prime R, sorry, alpha prime by R, alpha prime, and this once again becomes by R. And you notice then that if we identify N tilde is equal to W and W tilde is equal to N, if we make this identification,
Then a minus sign will come.
minus sign is needed. Okay. Then what do we find? We find that this becomes W and this becomes N, this becomes W and this becomes N, and so we see that x tilde left is equal to x left, but x tilde right is equal to minus x right. Okay? Now, W and R, W and N are just quantum numbers that run over all possible values. So, what we are saying is this, that the theory with radius R has the same x left as the theory with radius 1 by R, but has minus the x right as the theory with 1 by R. Once we do the suitable relabeling of labels which label the spectrum. Okay? Now the relabeling was interchanging winding and momentum. So once we interchange a momentum and winding, we find that the theory with x left, the theory with radius R has the same x left as the theory with radius 1 alpha prime by R, but has minus the x right as the theory with radius alpha prime by R. Now, so these two theories aren't exactly the same, because x left goes to x left, but x right goes to x right, minus x right. But for many purposes, they're basically the same thing. For instance, the spectrum is just the same, because a spectrum depends on PL squared and PR squared. What we see here is that PL goes to PL, but PR goes to minus PR. But for purposes of, say, the spectrum, it's just the same thing. Okay? So, these two theories are very closely connected. So basically what you do is you take a theory, break it up into x left and x r, right? And just flip the sign of x right. This is a symmetry operation that you can do because in any physical quantity you get x right squared. Like for instance in L0 there's x right squared. In all expressions that will be of interest to string theory, that x right term comes squared. Okay? Once we look at the superstring, we will have terms like x right times psi right. So we'll have to flip both x right as well as psi right. But once we do it consistently, for every quantity in the theory, for instance, the BRST charge and so on, okay, if everything appears quadratically, as we make sure that it does, okay, this is an effective symmetry of the theory. Okay? And so this symmetry operation, taking the theory, breaking it up into left moving and right moving part, and just flipping the sign of the right moving part, which doesn't change any quantity of interest to string theory, let's say the BRST charge or the Hamiltonian or any of that, okay, takes the theory of the theory on radius r and gives us the theory on radius alpha prime by r. Since as far as string theory is concerned, these two theories are the same, physically from the point of view of space-time, they should be regarded as the same theory. I will give you a better argument for this statement by the end of this class. You will see that the relationship between the theory and the T-dual theory from the point of view of space-time is that of gauge equivalence.
Gauge means deeper move.
No, it will mean some other gauge. I'll tell you as we go. But you will see from a purely space-time point of view that we have to regard these two theories as the same.
The sigma minus going to minus sigma minus will.
sigma minus goes to minus sigma minus. Yeah, but you know, sigma minus going to minus sigma minus will also take tau to minus tau. It's something you don't normally do.
Okay.
You know, you would have to do that here, but not
You
there.
do tau sigma exchange. Tau goes to sigma and sigma goes to tau.
Tau goes to sigma, but tau is time and sigma space. And, I mean, okay, you can you can try.
That's why I said
Diffeomorphism. Yeah, maybe in Euclidean space. Yeah, in Euclidean space, you can probably argue that from the path integral level, there's a clear symmetry. Okay. Okay. Yeah. Fine. Okay. Now, let us continue. Let us continue. Okay. So, this operation here is called Tduality. And it's the statement, as we've seen before, that in string theory, if you have strings propagating on a circle of radius r, you get the same physics as strings propagating on a circle of radius 1 by r, alpha prime by r. And in fact, the circle of radius alpha prime by r should not be thought of as distinct from the circle of radius r. These are actually the same theories. It's not. From the point of view of space-time, it's a clean argument. This is the case, which I'll try to come to by the end of this lecture. Okay? Excellent. Now, you see Tduality very clearly, of course, in the spectrum. Intuitively, what's going on? How does a small circle become a large circle? Intuitively, what's going on is the following.
But winding number is also changing.
What?
You're exchanging winding number and
Exactly. Exactly. That's how it works. Exactly. So, as Sunil said, if you had a small circle, momentum modes become very heavy, but winding modes become very light because you have to wind a very small distance. If you have a large circle, winding modes become very heavy, but momentum modes become very light. And so, if you interchange momentum and winding, it's not implausible that a small circle becomes the same as a large circle. Okay? In a small circle,
You are saying because of this 1 by r and r dependence, that winding mode are taking
exactly.
less momentum.
Exactly. If you looked at the Hamiltonian, the momentum mode was n squared by r squared, whereas the winding mode was w squared r squared. This is physically very clear, right? Because a winding mode is heavy because the string has to wind over a big circle. It's very light when a string has to wind over a small circle. Similarly, momentum is heavy when something has to go over a small circle because momentum is quantized in units of 1 by r. When r is small, 1 by r is very big. Okay? But momentum can be very light on a big circle because when r is big, 1 by r can be very small. Okay? So if we interchange your momentum, if you look at the momenta of a small circle, they behave exactly like the winding of a big circle. And the winding of a small circle behave exactly like the momenta of a big circle. So that's how it's working physically. Notice that the two extreme ends, r equals infinity and r equals 0, both have a continuum. When r is equal to infinity, you have a continuum of momentum modes. The gap between momentum modes goes to 0. When r equals 0, you have a continuum of winding modes. These two continua are identified with each other. Is this clear? Okay? Great. Fine. Now,
In r tends to infinity, there is a continuum in momentum also.
when r tends to infinity, there's continuum only in momentum. Winding, even if you take even winding 1, it's very heavy.
Oh, yes. Winding is exactly zero.
Yes, it's just set to 0.
You get some final.
Yeah. Whereas r tends to 0, it's a continuum in momentum, and momentum is set to 0. All good? Okay, excellent. So let's move. Now, there are two things we want to say about this. The first is about vertex operators. You remember that for the For the bosonic string, we had vertex operators, okay, and which we had written as e to the power I p x, maybe I k x. These are the momentum vertex operators, and then there were the vertex operators. Then we dressed these with the vertex operators for the oscillators. This was a vertex operator dual to the zero mode motion under the state operator map. Whereas when we but we had dressing with respect, then we also had the vertex operators dual to the oscillator motion. Okay, you remember that this guy had dimension alpha prime k squared by 4. L0 equal to alpha prime k squared by 4. That's the same as this formula, alpha prime p squared by 4. L0 and L0 bar were both was equal to L0 bar. Now, what will the vertex operators corresponding to the states with a particular n and L, or equivalently a particular PL and PR be? Well, in this case, K was just PL, which was equal to PR. So we just replace K by KL XL plus KR XL. Okay? So the vertex operator will be e to the power I. It's just the left moving part of the full free boson times e to the power I KR XR. Actually, this expression here has one small subtlety that's not correct. There's, in addition to this, there's what's called a cocycle factor. I will explain this cocycle factor. I will explain it to you for completeness by the end of this lecture, or maybe in the beginning of next lecture. But for now, because it's a technical thing, we'll go on for a moment, because it will enter almost no calculation you do. Maybe in some very involved calculation, it's important. Okay, I'll explain what that cocycle. This is you have to add one extra degree of freedom. I'll explain it to you. For now, just imagine this is correct. This is the small inaccuracy in the statement, which we'll correct. Okay. So this is the vertex operator where KL and KR are given by these formulas. Let's call it PL and PR. By those formulas. What is L0? Same formula. 0 is equal to alpha prime KL squared by 4, and L0 bar is equal to alpha prime KR squared by 4. These are these formulas. Okay. Now, these vertex operators give you something sort of interesting, which I now want to explain. Okay. The first question I'm going to ask is, what, under what okay, first we're going to ask, you have KL squared by 4, alpha prime KL squared by 4, which was equal to alpha prime into, let us remember, by 4 n by r plus wr by alpha prime the whole thing squared, and similarly with a minus. Now I'm going to ask, look, as you might remember, there was an interesting operator in this free boson theory which had L0 equals 1 and L0 bar equals 0. That was del x. And you remember from our discussion of current algebras, we argued that the set of all operators of this form, namely all operators with L0 equals 1 and L0 bar equals 0, were called currents. And there was an interesting operator product formula between them. This was the Kac-Moody algebra. Yeah. Okay? So far this free boson theory has a U1 Kashmodi algebra associated with it, because there is a single operator del x which is an L0 equals 1, L0 bar equals 0, L0 equals 1 current. Similarly for L0 bar, right, del bar. Now I'm going to ask, is there any other operator? Is there any other operator in this set of modes? Okay. Oh, by the way, before saying this, there's something I should have said. Remember, the operation of Tduality was alpha prime is r tilde was equal to alpha prime by r. Note that there is a special radius, square root alpha prime, at which the theory is T dual to itself. Okay, so there's one special radius we've encountered, namely where T duality takes the theory not to another theory, but back to itself. Okay, so square root alpha prime is a sort of interesting special radius. We'll keep that in mind. Okay, now we're going to ask the following question. We're going to ask the question, is there a theory, is there a special value of the radius and special values of n and w that at which L0 bar continues to be 0, but L0 is 1. So there's new current in the current algebra. So let's look. I'm clearing this out.
You are not looking at the cell-dual radius.
Not necessarily.
Okay, just for any arbitrary.
We look at it, explore, and see where this happens, where we land. Okay. So what we had was that remember that we had this was L0, and then there was alpha prime by 4 n by r minus w r by alpha prime squared. So the first thing is we want L0 bar to be equal to 0. Okay, so we want L0 bar is equal to 0, and therefore what we want is that n by w is equal to r squared by alpha prime. Right? Now, so let us substitute this in. Okay? So n by w is equal to r squared by alpha prime. So we'll substitute in here that r what?
Yeah, exactly. I mean, depending on what you want to do.
Yeah, 2n by r. I'm going to put r in, so I have everything in terms of integers. Okay, so I'm going to substitute in r is equal to square root of nw alpha prime, and then I'll put it into the formula for L0. Okay, so we have L0 then is equal to L0 is equal to let's see, alpha prime by 4 into n by so it will become square root nw, and alpha prime comes down, and of course this will just double because it cancelled, and that squares, so this goes away. Squared is equal to nw. Okay, but so we want n0 equals 1. Okay, so how's that going to work? The only way the product of two integers is equal to 1 is both of them are equal to 1, or both of them are equal to minus 1. So we have two options. We have n equals 1, w equals 1. or n is equal to 1 minus 1, w is equal to minus 1. In both cases, n by w was 1, and therefore r was fixed to be the self-dual radius. Okay? So, at the self-dual radius, we already saw something interesting happen, namely Tduality became self-symmetry. At the self-dual radius, we see something else interesting happens. And that other interesting thing is that, by the way, at the self-dual radius, PR squared was 0. And there, I mean, for this particular mode, PR squared was 0, therefore this PR was 0. And L0 was 1, so what did this guy amount to? Amounted to, this was equal to square root of 4 by alpha prime. So 2 by square root of alpha prime. KM. Okay. So I'm clearing this. Oh, maybe I'll clear this. Okay. So we have PL for these two modes, for these special modes, equal to plus minus 2 by square root of alpha prime, and PR is equal to 0. Of course, we have corresponding modes with just a relative sign difference. N is equal to 1, W equal to minus 1. N is equal to minus 1 and W equals. This is N W is equal to plus minus 1, 1. And then we have the modes with PL is equal to 0, PR is equal to plus minus 2 by square root alpha prime, and these are the modes with NW is equal to plus minus 1 minus 1. Okay, very good. Now, this self-dual point, therefore, we see is an interesting point. Let's try to understand better what's interesting about it. We see that both the left moving sector and the right moving sector have a current algebra with 3 currents. The 3 currents are e to the power I 2 by square root alpha prime, e to the power minus I xl 2 by square root alpha prime, and xl and del xl, and similarly for xl. What? One, there are 3.
This better be a SU2 or otherwise I'll be very disappointed.
Yes, definitely it's an SU. Okay. Now what we're going to do is to compute the OPs in the sector. Okay, so we're going to call this guy J plus, we'll call this guy J minus, I'll call this J3. Okay, and now what we want to do is to compute the OP in the sector. It's just the same old, the kind of thing that we've done always. Okay, so let's first compute what do we get when we take e to the power. So what are we interested in? We're interested in current algebra. So we're interested in the coefficient of terms that are 1 by z square, the coefficient of terms that are 1 by z, and anything else we can forget about. Okay, so let's first do the easy ones. let's do e to the power I 2 by square root of alpha prime xl with itself. Now let us remember. This was normal order, this, of course, I haven't written that. That's always what we need. Normal order this times normal order that. We want to write this as one whole normal ordered object. Okay? So when you expand out this thing, you will get, so it will be this times 2-point function. So e to the power minus, because of the I squared, 4 by alpha prime, because of the 2 by square root alpha prime, times 2-point function of xl with xl. Okay, now let us remember that the 2-point function of x with x of z with x of 0 was equal to, was it minus alpha prime by 2 log z squared? Z bar, yes. And therefore xl with xl is just z part. Okay? And so we get minus alpha prime by 2 log z. And so this becomes minus alpha prime alpha, so z squared. Nothing of interest. Z squared times completely normal order, and then there's a whole Taylor series expansion. Okay, but if we just flip one sign here, then that becomes 1 by z squared. We get 1 by z squared. Now that we have a 1 by z squared, we have to keep track of the next term as well. So 1 by z squared multiplies normal ordered e to the power I2 by square root alpha prime xl times e to the power. Okay, now let's be careful. This was at z, let's say, and this was at 0. Okay, so this is at z minus I2 by square root alpha prime xl of 0. Because it's within normal order sign, we can just Taylor expand like it is and like its numbers. Okay, so we just Taylor expand. So, I mean, we can Taylor expand up in the exponent first. So this xl here cancels this guy, apart from the fact that this was at z. So we get an extra factor of z del xl. Right? So this whole thing becomes I2 by square root alpha prime z del xl plus da da da. Nothing else will be important. We only need to keep one power of z. Expand that, we get I by square root alpha prime del xl by z. So we have now okay, and factors of 2, there was a 2, no, z. There was a 2.
There was a, yeah, that was a 2 and a z. 2i?
Yes, 2iz. Yes, there was a 2. So 2iz. Yes. So that's equal to 2jz. That's what we want, right? I mean, is this the standard SUP?
And j plus j minus is
2jz. Yeah. Exactly. And therefore we see that j plus of z, j minus of 0 is 1 by z squared plus 2jz by z. Okay, what remains is to compute the OPs between jz and other things. Let's first do jz with itself. That's very trivial, because jz with itself is minus 1 by alpha prime, because of the I by square root alpha prime. And then del x, we just use, it's del z minus del z squared, because one of them hits the 0, of minus alpha prime by 2 log z. log z. So that's equal to minus del z squared by 2. It's 3 minuses of 1 by of log z, and that is
1 by 2 z square. Is it 2, right?
1 by 2 z squared. Now this 2 is irritating me. But maybe that's okay, because the metric in plus minus is probably twice that of the metric in Cartesian, right? I mean, we wanted delta ij in Cartesian x and y, but j plus is jx plus ijy.
Yeah.
So you get a factor of 2, because jx contracts with jx, that gives 1, and the ijx contracts with minus ijy, so ijy contracts with minus ijy, which gives another 1. Fine. So we wanted that this thing appear with an overall factor of relative factor of 2. And what about the overall sign? Fine. Let's finish the calculation and then we'll see. Finally, so what did we conclude here? We concluded that J3 of 0 was like 1 by 2 z squared. And finally, we want J3 of z, J plus of 0. Okay. That is equal to I by square root alpha prime del x of z, then this is sum over m I2 by square root alpha prime to the power m x l to the power m by m factorial. Okay, now the usual story, this m cancels this m. We get an extra factor of this quantity out, so we get I by square root alpha prime. We get 2I by square root alpha prime. And then we get one factor of the contraction, which was minus alpha prime by 2z. Okay, and then e to the then j plus. The usual story, right? You guys all used to this by now. So the alpha primes cancel, so that's nice. Minuses cancel, 2's cancel. So we get J3 of z, J plus of 0 is J plus by z. But when we do the same with J minus, there's a minus because this comes with a minus. So J3 of z, J minus of 0 goes to minus J minus by z. This is z, not 2. Okay, and this here, did we get k by 2 in our Kac-Moody algebra? Where does Polchinski discuss Kac-Moody algebras? Probably in volume 2. I'll just check that the factor of 2 is the problem is that the analysis is so abstract. It's in terms of this highest root and squared and so on, there are factors of 2 all over the place. And I'll assume that when you work it out here, what we wanted was level by 2. Okay, and certainly that's the expected result. You know, this discussion in Polchinski's most general thing. It works for E8 and so on, but we might just have an SU2. So, okay. Anyway, this I'll leave as an exercise for you to check that if you go through that general analysis, which you remember we went through when we were discussing the heterotic string. Okay, you plug into that general analysis for SU2, you'll find that the current algebra was Jij was equal to k by 2, where k was the integer. Z squared plus
with the delta ij.
Yeah, delta ij. Yes, ij jk by z, and that's exactly what we've got there if you identify k with 1. Okay, so what we see is that we've got SU2 current algebra.
This delta ij means the metric.
Yeah.
I mean, plus will come with minus.
Plus will come with minus. This delta ij in Cartesian coordinates. Plus minus has now gone to complex coordinates. Right, so you transform the metric apparently. Okay, so we've got SU2 current algebra with k equals 1.
Or rather the group metric Gij.
That's
yeah.
better. Absolutely. Right, but it's the group metric normalized so that Jx with Jx is 1. Well, that's what I meant to say. Here. Okay, excellent. So what you see is that at the self-dual radius, what have we just shown? We've shown that at the self-dual radius, our string theory develops a current algebra. Okay, the worldsheet theory of the string of the self-dual radius develops a current algebra, and the current algebra is the current algebra of SU2 at level 1, both for the left and for the right. Is this clear? Okay, now we're going to try to see what implications this has for space-time. These currents are all very well, but they're entirely worldsheet constructs. Okay, how does it play into space-time? The way it plays in a space-time is this. Every time you have a 1-0 current, you remember that the full vertex operator had to be a 1,1 primary. But if you've got a 1-0 current, then you can take that and multiply by a 0,1 primary. Now the 0,1 primary in the bosonic string, so let's take, so we have let's say we do the following, e to the power I, okay, we take JL, we call it JL or JR, J plus minus L, left moving, okay, and for right moving we take del bar X. This works. This is a good vertex operator for string theory. So it represents a particle in space-time. Okay. Now this X here could of course be the X that we were talking about, but I'm going to look at the modes that for a moment are not that X, but the modes that are Xi, which are the non-compact directions. So suppose we've compactified one circle, we've got some non-compact directions. This is a possible vertex operator of the theory. Now, as far as the non-compact directions go, what kind of representation of the rotation group does this transform in? It's a vector. Right? Now, this can be addressed by e to the power I ki xi. This is a normal kind of ki because the xi's are non-compact. This guy already has L0 equals 1. This guy already has L0 bar equals 1. Therefore, this guy has to have L0 equals L0 bar is equal to 0. And therefore, we have to have ki squared is equal to 0. So, this is a massless mode.
don't have any k. This I.
Well, it can have
is
k.
the compact coordinate.
But it's not the compact coordinate.
But in kixi also.
Not the compact coordinate. All the zero mode dependence has been explicit here.
It don't have any momentum on the compact direction.
Nothing. I'm looking at modes which this is purely non-compact. This is, you see, because then it'll mess it up. Because then you've got a different operator here. I want to look at direct products of operators. This guy was purely in the X non-compact sector.
So ki square is equal to 0 and k compact is equal to 0 is.
K compact is.
K compact was what it was, right?
PLR.
K left was square
So
one.
the operator don't have that the compact direction xi, ki xi.
It has, this part had it. Right?
Okay, okay. That, I mean, I am saying e to the power ik.
No, it does not have.
Does not.
Does not have. It's just purely in the non-compact part. Okay, we can look at this as well as del x. So all three. Okay, now let us remember that so this mode is massless. It's clearly in a vector. So the most general operator will be epsilon I times del bar fxi. Be labeled by the polarization epsilon I. Let us remember that. The physical state condition tells us that that epsilon dot k is equal to 0. This came from the condition that L1 annihilated the operator. Let's remember why that is, because L1 had a piece which was P0i times alpha 1i. This operator here, I'm talking in the left, in the right moving sector. This is alpha tilde, alpha right. This operator here was alpha minus 1i on 0. So this, acting on that, this killed this and left with an epsilon. So it had P dotted with epsilon, and therefore P dot epsilon was equal to 0. Right, the condition of primarily primarity was that epsilon dot k was equal to 0. And it was also true that if epsilon was equal to ki, that was a null state. Why was that? Simply because take derivative of e to the power del bar derivative of e to the power I ki xi. What does that give you? It gives you I ki del xi e to the power ki xi. Now del bar derivative is clearly descendant, but that gives you this operator, but with epsilon replaced by ki. So epsilon being ki was a null state. You remember we discussed all this in great detail before. I'm just reminding you of this. Okay? And therefore, this object here is a vector which is massless. It's transversed to epsilon, and epsilon being shifted in the ki direction is to be identified with epsilon not being shifted. So what name can we give to this?
Photon.
It's a gauge boson.
Gauge boson, because it's SU2 now.
It's a gauge boson, exactly as you said. But, so we've got a gauge boson with some structure here on the left hand side. Okay? And if we now compute the whole OP, well, perhaps I can leave this for you as an exercise. Compute the 3-point string scattering amplitude. Now that we know about string scattering amplitudes, this is now an easy job. In fact, it's a trivial exercise. Okay, but anyway, I'll leave this to you as an exercise. Put in the ghost contributions. Okay, and compute the 3-point string scattering amplitude for these vertex operators. Okay, what you will see is that because you know you need the 3-point amplitude both on the left and on the right. But what is it on the left? It's this epsilon ijk. It's the structure constant. I'll leave it to you as an exercise to do. Okay? So, because you know j gives j by z. So take another inner product with a j. That j will contract away. There'll be z's left over, but they will cancel with all the z's from the c's. So that structure constant will remain, epsilon ijk. Okay? So what you will get is, what you will get is epsilon. So now what were our particles? Our particles are labeled by epsilon mu, which is a polarization index, and also a color index. Okay? That color index you can either keep explicit or dot with some color vector. Let's suppose we dot it with this, with a zeta I. Okay? So what we will get is epsilon ijk, zeta I, zeta j, zeta k times some momentum structure, which is precisely what you will get from taking f mu nu, expanding it to cubic order. Cubic because it's non-abelian gauge theory. So precisely the term you will get from a nu from one of the f's, and del mu a nu minus del mu mu from the other f and taking the trace. Because this AA has the epsilons, you know, if you put an A mu A here, you know what I mean, right? Because the AA has the epsilons, that's where the epsilons come from. And the momentum factors will be one factor of momentum, that will come from this side, from the right moving side. So I'll leave it for you as an exercise. Now that we are all experts at computing string scattering amplitudes, I'll leave it for you as an exercise to compute that the 3-point functions of these guys are precisely the 3-point functions that come out of the Yang-Mills-Lagrangian for an SU2 gauge theory. At low energies, the same is true also for 4-point functions and so on. But already this will be quite convincing. Okay. So what have we discovered? What we've discovered is that at the self-dual radius, the space-time theory has a new SU2 gauge symmetry. Now, at even away from the self-dual radius, our theory always had, by the way, the theory has SU2 times SU2.
For
left and right. Actually, even away from the self-dual radius, our theory always had U1 times U1, because there was del x and del x bar. Now, since this statement, anything that's true away from the self-dual radius as arbitrary radius is true at large radius, and therefore should have a field theory explanation. Nothing particularly stringy about it. So, the first question we should ask ourselves is, what was the explanation for that U1 times U1? Can anyone give me a suggestion?
Diffeomorphism along down the circle.
Very good. Very good. That's one of the U1s. And then there's the B field on the circle. Let me explain this to you. To you better. Okay. So now this is an interlude. Okay. We've discovered this SU2 times SU2 symmetry. We're going to try to understand it. Before looking at this complicated SU2 times SU2, which occurs only at the self-dual radius, we're first going to understand the U1 times U1 that occurs at every radius. Okay. So the first thing that we're going to try to understand is the following. We're going to understand the following fact. if we have if we have any gravitational theory compactified in a circle, when we look in the low energy effective theory, long distance competitive circle, there is always a U1 gauge field called the Kaluza-Klein gauge field. Okay, it's a very simple fact that I want to explain to you. So suppose we've got a gravitational theory with a metric that has a circle. We'll call that circle X10. Okay. So what I'm going to do is to do this. I'm going to look at configure. So now at low energies compared to the size of the circle, we're not allowed to vary. We're not allowed to move along the extend direction, because any motion in the extend direction has a minimum momentum 1 over the radius of that extend. But we want to be at energies low compared to 1 over r. So that momentum has to be 0. So we should limit ourselves to those configurations that maintain the translational invariance in extend. Okay? Now, the most general such configuration, most general such metric, okay, can be written as follows. E to the power 2 sigma times dx10 plus dx10 plus a mu dx mu. Mu is all the other directions apart from right. Plus g tilde mu nu dx mu dx mu. Where sigma, a mu and g tilde x mu are functions only of x mu's but not of extend. This metric clearly has translational invariance in the extend direction as a killing vector d by d extend. Okay. Now, the game that we want to play is to take this and plug it into Einstein's action and see what action that we get for the effective fields sigma, a mu and g mu. Now this is a game we can play, it's not too difficult, but even before playing that game there is a fact about the action as a function of x mu that is completely obvious, and that fact goes as follows. See, even though we're not allowed, because we're not allowed to change the fact that nothing depends on extend, we're not allowed, when now a set of coordinate transformations, which in general was x mu goes to any of the x's is a function of any of the others.
You're saying that extend goes to extend plus I of.
Very good, exactly. We're not allowed to do xi, x mu goes to x mu of extend, because that will introduce extend dependence. That breaks this form of the structure of the metric. But we are allowed to do, of course we're allowed to do x mu goes to x mu plus function of x mu. That's diffeomorphism in the low energy, in the remaining non-compact directions. But in addition, we're allowed to do extend goes to extend plus, as Schumann said, extend goes to extend plus del
High of x mu.
plus phi of x. Okay. Now suppose we do this. Under this, what can we do to keep the form of the metric unchanged? Well, this changes to del mu extend plus del mu phi of x mu. Under this change.
But dxten
Dxten goes to dxten
plus del mu dx mu.
del mu
X.
times dxten.
Del mu.
No, I mean that's.
Yeah, del mu extend.
No, that's not del mu extend.
Well,
I mean, in the sense that dxten goes to dxten plus del mu
right.
phi dx mu.
Yeah, d extend is del mu extend, right?
Yeah.
Yeah. Right, that del mu extend there was del mu extend plus d mu.
Right.
Fine. But that can be cancelled
with minus.
if A mu goes to A mu minus d mu phi of x mu. Now, so this tells you that the following two configurations, the configuration with A mu and the configuration with A mu minus d mu phi of x mu, are the same configuration. They're diffeomorphically related. Because a diffeomorphism takes you from one to the other. Is this clear? Therefore, the action for one configuration has to be the action for the other configuration. Therefore, the action has to be invariant under this transformation. Therefore, the action has to have a gauge invariance. Einstein action is two derivative. There is a unique gauge invariant two derivative action. With the symmetry, it will be f mu nu, f mu nu. And then there will be some e to the power sigma business outside. All those are details. The fact is that you're going to get a f mu nu, f mu nu. You can see that from general principles without doing any calculation. Just a consequence of the underlying diffeomorphism invariance. Okay? So what we've seen here is that if you take gravity and you put it in a scalar and you look at long distances, okay, you get a massless photon, actually a massless scalar. Why is it massless? It's massless because you can shift that scalar to anything. Because changing that scalar is just changing the compactification radius of x10 effectively. But flat space with a circle of any radius of compactification is a solution of Einstein's equations. Therefore, there is no mass for sigma because there's flat direction. Solutions with every value of a constant value of sigma. Yeah. So, massless scalar, massless photon, and a lower dimensional metric. We can work on the details later on, but it's clear on general grounds that this is the form of the action depicted. So whenever you have gravity in a theory with a circle, you have one massless gauge field. This is called the Kaluza-Klein gauge field. It's got a very simple origin, as you've seen. Is this clear? Well, it's a massless gauge field. Now, what we assumed was that there was no dependence on the other directions. When you correct that, what you will get is in addition to this massive modes, because you get Kaluza-Klein modes. Right, what I have done is take all fields and put them zero mode around here. But in general, they could be in momentum 1 or momentum 2 or momentum 3 or momentum 4. That won't change the fact that this exists. It will only add additional massive modes. In fact, the interesting thing that I haven't shown you here is that you can ask, what is the charge for this A mu? What particles are charged under A mu? And the answer to that question, well, is obvious. You see, what was the thing that shifted under gauge transformations? It was x10. So suppose I have e to the power I m x10. Then under the same shift, how will this transform? It will pick up a factor of e to the power I m phi. So this is a particle of a charged field with charge m. So momentum in the 10th direction is charge for the Kaluza-Klein gauge field. So these heavy modes that you're talking about will all be charged fields. Is this clear? By going to the low energy sector, we're just ignoring all the massive charge fields. But we're not making an approximation. We're not making the approximation that this exists. The fact that this was massless made it self-consistent to look at it at low energies. Because massless modes can be studied at low energies. Is this clear? Okay? So this was one of the U1s in the theory. Now what about the second U1? The second U1 was the fact that string theory, there wasn't just the metric, there was also the B mu nu field.
Are you saying that there was one direction which was always compactified?
Yeah, I'm saying that suppose we started with one direction compact, but not necessarily at self-dual radius. See, what is the observation we're trying to explain? We're trying to explain that if you start with a compact direction, then there are two u1s at any value of the radius, because you have del x and del by x. So we're starting with some compactified radius, not necessarily at a particular radius. We want to understand why this always has two gauge fields. Is this clear? Okay. Now, because we can work at any value of the radius, we go to very large values of the radius. Since it's large compared to string units, field theory, just classical, general relativity should be correct. So we should have a simple intuitive understanding of this fact based on familiar physics. This is what we're trying to find. Is this clear? Okay. We've understood one of the two u1s, but we got two. What about the second one? Well, you can really actually, the fact that this is what's going on is clear from the vertex operator as well. Because you see, what we got is we took del x10 del xi. Let me explain better. What were our vertex operators that gave us the massless modes? They were JL, JR, and del x10. Away from the special radius, it's only del x10. So our vertex operators were this, then del xi, and then e to the pi k xi. Okay? So what we got was del x10 del xi. So that is sort of like the off-diagonal component of the metric. More precisely, if we symmetrized it, it would be the off-diagonal component of the metric. And this a mu is precisely the off-diagonal component of the metric, because one extend term and one dx mu term. Okay? So at the algebraic level, we see that our explanation is matching, but we see that that explanation that we have here matches only when we symmetrize this. That is, when we take del x10 del bar xi plus del xi del bar x10. That would match the metric. But in our explanation, we didn't need to symmetrize, and that's why we got two, right? The second one you could think of as del x10 del bar xi minus del xi del bar x10.
The B field.
Exactly. The linear combinations of these two gives us the two u1, the one that was purely left moving and purely
The B
right.
field with one leg in the compact and another in the non-compact.
Exactly. The B field with one leg compact and one leg non-compact. Now, why did that also give a gauge field? There the answer is even simpler than before. You see, B mu nu had a gauge invariance. And the B mu nu goes to B mu nu plus del mu chi nu minus del mu chi nu. B goes to B plus dA, where A is a 1 form, d chi is a 1 form. Okay. Now, once again, let's take this configuration where we had 10 and I. Once again, our chi's are only allowed to be functions of I. But nobody stops us from choosing also a chi 10. Okay? Suppose we chose a chi not equal to 10, a chi mu. Then this will be purely in the mu nu directions.
Yeah.
Because derivatives are only in the mu nu direction and chi is also in the mu nu direction.
Yeah.
But suppose we choose a chi 10. Then the del 10 chi mu is 0, because del 10 of anything is 0. But the del mu chi 10 is non-zero.
And the B I10 will transform like
Yeah, and therefore we see that B mu 10 goes to B mu 10 plus del mu chi10. And that's a gauge invariance for B mu 10. Therefore, B mu 10 is another gauge field. And if you build the action has to appear only through its field strength. So there's another U1 gauge field in the game. These were the two U1s that came from these two obvious vertex operators, the del x10 and the del xi. Is this clear to everyone? So the U1 times U1 that we saw in this construction is completely obvious. It's obvious right from the beginning from low energy considerations. What is a surprise is that at the self-dual radius this gets enhanced to SU2 times SU2. Okay. Now, the last thing I want to do is and you can ask, why does it get enhanced to SU2 times SU2? Well, there's no answer to that in terms of low energy field theory. Because we're at the point where no description, neither the description itself nor the Tdual description, is at long radius compared to string scale. This is a purely stringy effect. It's a new thing. However, it has consequences. Okay. And the consequence that I want to look at is the following. Okay, this is the last thing we'll do this lecture. The consequence that I want to look at is the following. So far we have looked at the vertex operators that were JL times del x del by xi, so JL plus minus or JL3 del by xi. Okay. I won't keep writing these. JL means all of them. I'll call it JLA. These were good vertex operators. That's great. They were good because everything was massless. And similarly the other guys. But there's another obvious set of vertex operators. And these are, which are also dual to massless fields. JLA, JRB, e to the pi kxi. This is 1, 1. Therefore, this must be 0. And therefore, ki squared is equal to 0. Okay. Now, what can we say about these guys? Firstly, what kind of objects are they under the Lorentz group of the non-compact part of the scalars? They're scalars because they've got no indices. They've got internal indices, but from the non-compact direction, that's nothing. Okay, excellent. Next question. How do they transform under the two SU2s?
They transform as tensor of
as 3 cross. It's a 3 under the first SU2.
Yeah.
They transform just like the J's transform. So adjoint times adjoint.
Yeah.
They adjoint under the first SU2
Yeah.
and adjoint under the second SU2.
Yeah.
In fact, the best way to think of this is a matrix. MAB. Let's call this B tilde. So that the first index transforms like a 3-dimensional representation of the first SU2. And the second index transforms like a 3-dimensional representation of the second SU2. Okay? Now, let me first focus on the object M33. Where is that? That's del x10 del by x10. Where? Louder? Reduce. Del x10 del by x10. That's clear? Because 3 was this, 3 bar was this. Now, I want to know what is the interpretation? Suppose I take, first, okay, the various things to say. The first thing to say is this, okay? We've got a set of 3 times 3, so 9 massless scalars at this self-dual point. Now if you've got a massless scalar, you've got 2 options. One option is that its potential looks like this, that its quadratic term vanishes but its quartic term does not, or some higher order term does not. The second qualitative option is that it's just flat. Okay? All of these 9 scalars give you are massless. So there is this space that I'm drawing here, some 9-dimensional space. It's a potential for 9 fields. Okay? In every direction around, expanding around the origin, you've got no quadratic term. Interesting question, are there quartic terms? Or does this continue forever? Now, what does this correspond to from the point of view of worldsheet string theory? From worldsheet string theory, it's the question that we are asking is, if we add a little bit of the scalar, does that still give you a worldsheet string theory or not? You add a little bit of the vertex operator, scalar vertex operator, to the worldsheet action. Does that deformed action, deformed by the vertex operator of that scalar,
whether it's some instability or not, I mean
whether it's an exactly marginal direction or not. Because you see, suppose it was a flat potential, then we could be either here or here. Each of these positions should be described by a new worldsheet string theory. But going from here to here is just adding a little bit of the vertex operator for the scalar. So it should be that just adding a little bit of the vertex operator for the scalar keeps the theory conformal. But an operator added to a conformal field theory which keeps it conformal has a name, it's called a marginal operator. So we are asking, are the vertex operators corresponding to these flat directions marginal or not? Exactly marginal or not? Now of course, the answer may, because we've got many vertex operators, there's a 9-dimensional space. The answer may depend on which direction we move in. Okay? Now I'm working out an example. Let me move in this particular direction. So suppose I had del x10, del bar x10, and I added this was my Lagrangian, right? In the extended. I added this with some infinitesimal coupling. What I get is 1 plus epsilon times this. Now if I redefine the field x10, I can get rid of this epsilon at the price of what?
the periodicity.
Exactly, changing the periodicity. So turning on the vertex operator with some epsilon is equivalent to changing the radius. But we know this is exactly marginal, because compact scalars are good conformal field theories at every value of the radius. So this is an exactly marginal deformation. So there's at least one exactly flat direction. Okay?
And this exactly flat. So everywhere in the moduli space, this remains a flat.
That's a good conformal field theory.
Yeah.
Okay? But now there is something here very, I see. Okay, so now what we've got is a new picture.
So there will be 8 peaks plus.
Yeah, you'll see. The counting is not exactly 8, but along the lines of what you see. Suppose we're at the self-dual point here. Turning on, going to larger radius is turning on the vertex operator with positive epsilon, let's say. Whereas going to smaller radius is turning on the vertex operator, that same x33 vertex operator, with negative epsilon. But now, look, J3 and minus J3 are gauge equivalent. because J3 is an arrow in the z direction. And a 180-degree rotation in the xz plane turns it into an arrow in the minus z direction. Okay? So an infinitesimal addition with epsilon is the same as an infinitesimal addition, is gauge equivalent in the bulk to an infinitesimal addition of the scalar, changing of this vertex operator, with minus epsilon.
That's also the statement of Tduality, right? I mean, any small radius is equivalent to a slightly larger radius.
And it's precisely the statement of Tduality, because to leading order in epsilon, 1 over 1 plus epsilon is equal to 1 minus epsilon. See, with numbers it works. But what have we learned from this? We've learned that the circle of radius a little less, so the infinitesimal Tduality operation, from the point of view of space-time, you could do this operation using a gauge symmetry. Now what do we know about gauge symmetries? We know that gauge symmetries aren't symmetries, they're just redundancies of description. Two configurations that are related by a gauge symmetry should not be thought of as different configurations, they're the same configuration. And therefore we see that from the point of view of space-time, a theory on a circle alpha prime by r is not a different configuration from a theory on the circle r. It's the same configuration, just viewed in a different gauge. Okay? So Tduality is a fantastic thing. It's a gauge symmetry. It's a redundancy of description. It tells you that there is no meaning to compactifying string theory in a circle of radius less than alpha prime by r. You think you're doing something new, but it's not even that you're going to something symmetry related to what you had before, it's you're going back to the same configuration. The set of radius compactification stops at alpha prime by r, at square root alpha prime. Is this clear? Now, the last question I'm going to ask is what we can say about this MAB field, what we can say about the potential of this MAB field more generally speaking. Okay? Potential is the same as the question as a beta function on the world sheet of the string. Exactly what the connection between the two is, I will explain to you at a later point. Okay, from the space-time potential of the world sheet beta function, what can it be? Well, you see this world sheet potential, let's think of it from the space-time potential, it's a bit easier to think. This object has to be something that is invariant under both SU2s. Note that the SU2 that multiplies the matrix on the left has nothing to do with the SU2 that multiplies the matrix on the right. Now, you know, had it been that there was the same SU2s, then you could write down trace m to the power k for any k. That would be gauge invariant. But this is not gauge invariant. Are you understanding me? No. You see, this object here is a gauge variant object. Potential is always gauge invariant. I want to write, I'm asking you, try to imagine any potential you can that is invariant separately under SU2 transformations on the left and on the right. Okay? Now, there is a simpler problem, a problem where you have adjoint gauge fields, adjoint scalar fields, such that this transforms like something inverse. When you have that, trace of m to the power k is a nice gauge invariant potential, because the something and the something inverses cancel in the middle, and because of the trace it cancels at the ends. That's nice and gauge invariant. But this doesn't work because we have something and something else inverse. Now, so can you think of any object at all that is gauge invariant? Any potential you can write down that is gauge invariant under both SU2s? Very good. Very good. The determinant works. Look at det M. If you look at determinant of M has the property that det AMB is equal to det A det M det B. But since A and B are both SU2 matrices, both their determinants are 1. And so the determinant is an object that is invariant under both SU2s, and indeed basically the most general potential should be any function of the determinant. Now if you have any function of the determinant, the most general function of the determinant, the most general, I mean to leading order function of the determinant will be det M itself. Okay? This by the way is cubic because we've got a 3 cross 3 matrix. Okay? Now we'll see in the next class how all this changes in the superstring. So far we're just working the bosonic string. But anyway, at the moment this is cubic. Okay? Now let us assume that the potential, that there's no special, nothing special happens. That the potential when you compute it, or the beta function when you compute it, has the coefficient of det M is non-zero. That would be consistent with masslessness because the potential would be cubic. Okay? If that is the case, then exercise. Compute the equations of motion that follows from this potential, which vary the potential with respect to all fields, and show that every solution to the equation of motion, every flat direction, is gauge equivalent to M33. It's obvious that M33 is a solution. Why is that? It's because determinant is cubic. So you take an equation of motion, you'll get something quartic. But if only M33 is non-zero, every quartic expression, no term appears twice in the determinant. So every quartic expression is 0. So once you vary and you set on M33, you evaluate that variation on M33, you'll get 0. Obviously there's nothing special about M33. It's just M with any vector dotted with the same vector. It's true. These are the gauge transforms of M33. Okay, or more generally M with one vector here, other vector there, it's also true. These are also gauge transforms of M33. Okay, but anything that is quadratic or higher, any object, if you have, so what, you know, so I've got a determinant, and basically if I've got M33, it's got rank 1. All rank 1 matrices are gauge equivalent to each other. But you could have instead rank 2 matrices or rank 3 matrices. The exercise is basically to check that if you vary this determinant M, evaluate on a rank 2 matrix or a rank 3 matrix, you will always get 0. I mean, you'll never get 0. Okay? So the only flat directions, the only exactly flat directions are these circle compactifications. I mean, changing the radius of the circle. Okay? So that's a bit disappointing because you might think that we would have discovered new conformal field theories. So, you know, to end today's lecture, I'll plot it in the direction that Polchinski likes. Horizontal direction. What we've looked at is the space of conformal field theories involving one scalar field and compactifications, and we found that naively it was a line that went from one end to the other, or at least a line that went up to 0. But here it ends instead at square root alpha prime. You try to go further, you go back to the same point. And here there are new massless modes. So potentially new conformal field theory is coming out. Okay? Here there are potentially new conformal field theories coming out, but unfortunately none of them are exactly marginal directions. The only exactly marginal direction is going back, is gauge equivalent to going back along this line. Okay, so we didn't discover new conformal field theories by looking at this interesting SU2 point and perturbing in some other direction. Is this clear? Okay, now the last thing I wanted to say in today's lecture was something that Upmanyu already alluded to, namely what happens what happened to the okay, at the self-dual point we had two things. We had 6 massless gauge bosons and we had 9 massless scalars. Okay. Now, a little bit away from the self-dual point, the massless gauge bosons have all become massive because they no longer have k square equals 0, because this is no longer 1, 0 operator. Right? So, for
Except for one.
What? Yeah, you're absolutely right. So, that's right. So, of the 6 massless gauge bosons, 4 have become massive. Okay? And also, the spectrum of massless scalars has changed. So, the exercise I have for you guys is the following. Interpret this in terms of the Higgs mechanism. See, away from the self-dual point, what we've done is to take this gauge theory, which had SU2 times SU2, and break it down to U1 times U1 with a wave of a guy that was in the 3-3 of this SU2 times SU2. Now, as you know, when you do that, you can transfer some of the degrees of freedom from the scalar sector to the vector sector. The transferring makes the previously massless gauge bosons, which had one less degree of freedom, massive, and removes some of the degrees of freedom from the scalars. Give me a clear interpretation, clear counting interpretation of this fact by next class in terms of degrees of freedom. Okay, fine. That's it for today. As far as the bosonic string is concerned, that's all we're going to say about just compactified closed strings. In the next class, we will study 2 things. We will study orbifolds of the bosonic string. That's an interesting thing. Sticking so far at this point, up to this point, still within closed string sector. Then we will study both orbifolds, but especially Tduality with open strings. And then we will see how all of this generalizes to the superstring.